Episode 7 Effect Pigments, Metallics and Pearls Visual Effects and Orientation Control in Automotive Coatings. In this episode, we focus on effect pigments, including metallic and pearlescent pigments, which are critical for achieving the visual effects that define premium automotive coatings. Unlike conventional pigments, effect pigments do not rely solely on absorption or scattering of light. Instead, they manipulate reflection, refraction, and interference of light to create brightness, flop, color travel, and depth in automotive finishes. Understanding their behavior requires a careful examination of particle morphology, orientation, surface treatment, and interaction with the binder system. Metallic effect pigments are typically made from aluminum or aluminum alloys, coated with inorganic or organic layers to improve chemical stability, prevent oxidation, and optimize visual performance. These pigments are essentially microscopic flakes, often tens of micrometers in lateral dimension, but only a fraction of a micrometer in thickness. The aspect ratio, flatness, and smoothness of these flakes determine how they reflect light and produce a metallic appearance. Pearlescent pigments, on the other hand, are generally mica-based substrates coated with thin layers of titanium dioxide, iron oxide, or other metal oxides. The interference of light within these thin films produces the characteristic pearl-like shimmer and color shift. The thickness of the coating layer, the refractive index contrast, and the uniformity of the deposition are critical parameters controlling color intensity, angle-dependent color change, and brightness. Orientation of effect pigments during application is the single most important factor in achieving the desired visual effect. In a liquid coating, flakes are randomly suspended initially. As the coating levels and the solvent evaporates, flakes tend to align parallel to the substrate due to gravity, flow, and surface tension forces. Optimal alignment maximizes specular reflection, creating brightness and a metallic sheen. Poor alignment causes haze, reduced flop, and inconsistent appearance, which are common defects in effect coatings. Binder viscosity, flow, and surface energy strongly influence flake orientation. Low viscosity binders allow easier flake alignment but may lead to sagging and settling, while high viscosity binders improve stability but resist flake rotation, reducing brightness. Formulators often adjust solvent blend, rheology modifiers, and leveling agents to achieve a balance between flake orientation, application properties, and surface smoothness. Surface treatment of metallic and pearlescent flakes is also critical. Uncoated aluminum or mica particles are highly reactive and can oxidize, corrode, or chemically interact with other formulation components. Coatings protect the flakes, control optical properties, improve dispersion, and enhance compatibility with binders. The choice of surface treatment affects not only stability but also adhesion, wetting, and final appearance. Effect pigments are highly sensitive to layer thickness. Too thin a layer may produce insufficient reflection and muted effect, while too thick a layer can cause excessive flop, streaking, or shadowing. In multi-layer automotive systems, the interaction between base coat, effect pigment layer, and clear coat must be carefully controlled to achieve consistent visual performance under varying viewing angles and lighting conditions. Dispersion is another challenge. Agglomeration of flakes reduces effective surface area, causes haze, and can lead to defects such as fish eyes, pinholes, or orange peel. Controlled milling and specialized dispersants are used to separate flakes without damaging their structure. Unlike conventional pigments, breaking down flakes is counterproductive, as it reduces their optical effect. Effect pigments also interact with other pigments in the formulation. Background opacity, color tone, and gloss are influenced by supporting pigments such as titanium dioxide, carbon black, or organic colorants. For example, a darkened base enhances metallic contrast, while a bright base maximizes shimmer. Formulators must carefully balance the ratio of effect to supporting pigments to achieve the intended visual effect. In addition to optical properties, effect pigments influence rheology and application behavior. High aspect ratio flakes increase viscosity and can impart thixotropy, improving sag resistance during vertical application. However, excessive loading or poor wetting can increase spray defects and reduce leveling. Achieving uniform orientation requires optimizing formulation rheology, application method, and flash-off conditions. Durability is also a concern. Metallic flakes are prone to corrosion if unprotected, and pearlescent pigments can delaminate or dull under UV exposure. Proper surface treatment, binder compatibility, and protective clear coats are essential to maintain visual effects over the lifetime of the vehicle. In summary, effect pigments are highly engineered particles that control reflection, interference, and visual effects in automotive coatings. Their performance depends on particle type, morphology, surface treatment, dispersion, orientation, and interaction with the binder and supporting pigments. Mastery of effect pigment behavior is essential to achieving the distinctive metallic, pearlescent, and color travel finishes that define premium automotive paint systems. If you have any doubts about metallic or pearlescent pigments, their orientation, or how to optimize visual effects in automotive coatings, leave your questions in the comments and let me know.